All right, folks, welcome to week 4. Um, Specifically, we're going to start getting into the next part of the diagramming, which is the logical and physical diagramming. I did give you guys like the 10-second demo last week, right at the end, using Vertibello. Um, I'm going to still do another example at the end today that's a little more fleshed out so that you have a better example. But we have some theory type stuff to do first. Um, Quick refresher on what the different keys are. Primary key, used to uniquely identify a row in a table. You guys should know this by now, I hope. A foreign key, it's a key that exists between two tables to enforce, foreign integrity. A compound key is a key made up of two or more columns. A surrogate key, also called a computed key, or there's another word for it. But anyways, surrogate key is the official term. It's an artificial key that's used as a primary key. So these are, it's generated by the database server. So that's when you use an auto increment column of some sort. Your student numbers are a perfect example of a surrogate key because it has no real world meaning and it's generated by the system. It has a real world meaning to each of you, but realistically that number doesn't actually mean anything. It's just a number, right? Now, the thing is that when we talk about keys, it can be a combination of any of the above. So a primary key could also be a foreign key. It could be a compound key. It could also be a surrogate key. That's part of a compound key. So when you start talking about keys in a database server, you can't just say, oh, it's a key. You actually have to be precise and identify what kind of key it is, because your primary key can often be a compound key. Usually when it's a compound key, it usually involves a foreign key. So you could actually have a primary key that is a foreign key that is a compound key. That's actually was very common back in the dark ages of computing, when computers had limitations and disk space was actually a concern and that kind of stuff. You tended to see a lot more of these compound primary keys that were also foreign keys because you were trying to reduce the amount of data in your database and you were reusing as much information as you could. So still talking about keys, we have two kinds of keys that tend to get used for primary keys. We have surrogate keys and natural keys. Now, a natural key is a key based on a piece of data that comes in from the outside of the database server. An example of those would be your SIN number, your passport number, your phone number, your email address. Those are natural keys because they come from a data source that's external to the database server. You'll hear old-time database people talk about the good parts of natural keys, such as reducing the number of columns. It tends to be more meaningful because it's holding a real value. However, those of us that have accepted the fact that the modern world is not as nice as it used to be, especially when it comes to people's information, and by the way, it was never nice. It was just a lot harder to get it. Natural keys can be complex because, for example, you can't use a person's name as a key because names get repeated. Depending what part of the world you come from, your name may be repeated many times. Strange fact, I'm the only Daniel Goudreau that works at Health Canada, which surprised me because my name is actually one of the most common, my first name is one of the most common Goudreau names you'll get. Don't know why. Um, but it was, but at Health Canada, I'm the only Daniel Goudreau, but there's actually other Daniel Goudreaus in other government agencies. So you can't use a person's name as a key, so you have to use a person's name plus something else. That means the key's getting more and more complicated. It can be slow. Computers are really good at numbers. They suck at strings. Strings are slow, especially when you start mixing in other character sets. It gone really fast on, the standard Latin alphabet, right? So your standard A to C, A to Z, uppercase, lowercase. And let's throw in some Cyrillic into the mix, you know, throw in some moon runes from insert preferred Asian country here, and suddenly everything gets slow because it takes so much more work to figure it out. I mean, when you are source searching through a database and suddenly you got an A, you got a number, you got a B, suddenly you've got, you know, the Chinese character for dog with two tails in there. And suddenly, what has that, it's got to figure out what that means in the sort order, and it makes it difficult. It can be difficult to update. Systems that use your email address as your primary key, and those exist a fair amount. Um, what happens if a person's email address changes? Now I used to be able to ask this, and it was actually one where I had more people that would say yes, but how many of you have had more than one email address as your personal primary email address in your life? So a fair amount. The Gmail generation, they're like, I've always had the same Gmail account since day one. I may have different aliases, but it's been the same Gmail email address since day one. For those of us that remember the dark ages of internet where your email address is whatever your provider gave you, I had an old email address at concentric.net. That provider doesn't exist anymore. Then it was like something at iStop. And then I got one from Bell that I never used because by then I was on Gmail. But I mean, in my life, I've had 6 primary email addresses because every time I moved from North Bay to here. Guess what? I had to get a new provider. I got a new email address. Then I moved from one part of town to the other part of town, and for some unknown reason, my provider wasn't available in that part of town. So I got a different email address, and then I went to Rogers for high-speed cable internet, 3 megabit. It was amazing at the time, but compared to dial-up, but I got another email address, then I switched to Bell Fiber. Not Bell Fiber, sorry, Bell DSL. Guess what? I got another email address. By then I was like done, right? I was on Gmail and I was never changing it ever again. And I've been on Gmail for so long that my email address doesn't have any numbers in it. It gives you an idea how long I've had it. But that can be difficult to update because if your email address changes, that means you got to cascade through the system and update all these primary keys, which is not easy. And then this is the one I like to talk about. It leads to privacy and security issues. Let's say you're using your SIN number as your primary key, which, by the way, the CRA uses your SIN number as your primary key. I wonder why. Obviously, because you're only supposed to have one SIN number, and it's probably just you. However, that leads to privacy and security issues, because imagine if you're here at the school, and for some unknown reason, the school decides to use your SIN number as your unique identifier. So that would mean that anybody who can see your student number, which is now your SIN number, knows what your SIN number is, and now they got all the they have all the information they need to fake you. They know your name, your SIN number, and all that fun stuff. Natural keys are nice because they're human understandable, but they have a lot of issues, performance issues and security and privacy and that kind of stuff. Or even people that use the credit card number as a primary key. Banks use your bank card number as your identifier. Not anymore. Like card's tied to you, but it's not your unique identifier. It's actually your bank account number. But even that's not quite how it works. Depends which bank you're talking to. It gets complicated. So modern database design tends to stay away from natural keys. It's just better that way. Now, surrogate keys, which are artificial keys, they're generated by the system. They are really fast on searches and joins. Why? They're numbers, right? Computers are really good at numbers. They're really fast at figuring out numbers. And if you're just joining across numbers, doing a join from one table to the other, and it's using numbers, the join's going to be faster than if it has to go like your email address. Then it's got to compare every character of every email address when it's doing the join. It's not just saying, oh, email address A is equal to email address B. It's going, is letter 1 the same as letter 1? Is letter 2 the same as letter 2? 3, 4, 5. A little more efficiently than that, but that's basically what it's doing. So those are slow because it has to compare every value in the field as part of the join. Whereas if it's doing a number, it doesn't need to look at is it 11? It doesn't look is the first digit 1, is the second digit 1. It says is it 11 because the computer knows it's a number. Surrogate keys do not care about privacy issues because the number doesn't actually mean anything. This is where my example of the student number falls over a little bit because here at the school, your student number is how the school identifies you, so it has meaning in the real world. But true surrogate keys have no meaning in the real world. They're just numbers that are automatically assigned by the database server. The end user never needs to care about it. And, if I just go, I go to you, I go 1,533. What does that mean? You don't even know what I'm talking about. Just 1,533. It has no real world meaning, so it has no issues about privacy or security. You'll hear some people complain a little bit that it has no business meaning. In other words, surrogate keys have no real world meaning, therefore it has no business meaning. Who cares? Like, honestly, who cares? Some people say, well, it's not that handy because it doesn't have any meaning. Now, how many of you have had, would you just ask me something? No? Okay. I thought I heard something, but between the noise out there, it's hard to tell. Yeah, it is. Like, they'll be used in a business, like an invoice number is a surrogate key. It's a number that's generated. Your receipt number is generated. There's no business meaning before it comes into the real world. Your student number has no business meaning until it's assigned to you. Then it has value. So honestly, a lot of people argue about it, and it's a pointless argument because whether or not it has real world meaning is relevant. So it's a better system. Now, this one is valid. The next point they use is that there's more data being stored. Yes. You're adding a numeric column. So you're adding one more piece of data. By the way, the space taken for one letter, which just so you know, if it's just the standard basic alphabet, one letter is 8 bits, right? So the letter A occupies 8 bits. For 8 bits, you can store up to the number 200. Hang on. 6, 7, 8. So I'm only at 4 bits, I'm up to 8. 16, 32, 64, 256. Right? So for the letter A, you can actually store 256 numbers in the same space. So yes, it has more data, but it's much more efficient data. Also for indexes, people complain that it will add an extra index because the primary key is always indexed. And if you're fabricating a primary key, you're adding one more index to use up a little more room on the database, on the disk, et cetera, et cetera. But then again, the index on a number is significantly smaller than the index on an email address because 256 fits in 8 bits, right? Whereas letter A is also 8 bits. And if you're talking about the full alphabet, it's actually a byte. So, and then you'll hear people complain that it's ugly. The purists said, I just want just the pure data, and it will complain that it's ugly because it's just a number and it has no meaning. So it's ugly. Whatever. All right. So that's the keys. I'm pretty sure, by the way, I was talking, which side of the fence on the surrogate versus natural keys I sit. Definitely not on the side of the natural keys. I've inherited too many systems where there's natural keys where we actually had to take them out because of privacy reasons. We actually had to rewrite entire parts of the database and, migrate data and rewrite applications because of that. So yeah, surrogate keys, that's the way to go. So the next topic we have for logical design is resolving complex relationships. So far you guys understand the concept of one-to-one. That's fairly straightforward. It's not a complex relationship. One-to-many, you also understand that it's not complex. Many. It's when we talk about many to many, they are significantly more complex to deal with because they're physically impossible in pretty much all RDBMS systems. We're not talking about NoSQL non-relational systems because those don't care what you do with the data. You take data, you put it in there, and it goes, cool. It doesn't even understand the data. It doesn't care to understand. Many to many is physically impossible to actually implement in a modern database system. So you resolve the many to many by creating either an intersection or an associative entity. They have two different jobs. So if we're talking about the conceptual diagram where entity A is related to B many times and B is related to A many times, it would get resolved as follows in the bottom. Now, A is related 0 or more times to B, and B is related 1 or more times to A. So when you go to resolve it, you create a new entity in the middle. Okay? Entity A and entity B love each other and they have a baby. And the baby has DNA from both sides. Okay, it's a pretty graphic example, but that's pretty much what happens, okay? So has 0 or more entries in AB. B always has an entry in AB. That's how we take this line becomes here. This line goes here. So if you actually want to physically see me do that, it's, this becomes this. Really, right? So you got a line that's like this, right? Many, many both ends. You end up with one at each end with pointing to the many in the middle. So that's physically Dan showing you how it happens, right? So the many to many is resolved into, it becomes a pair of one to manys with a child table in the middle. Now, let's just talk about it on the next slide before I keep talking. Okay, so at this point in time, this here is either an intersection or an associative, because we haven't put any attributes or columns in it, right? So it's basically what they call an intersection table. Now, an intersection table only has two columns. Well, I have to be careful when I say only two columns. It only has the primary keys of the parents. So if we're going with surrogate keys, which is, I was telling you guys that's the way you should be doing it, each of the parent tables will only ever have one key, one column. So that means the child table will have two columns. The primary key from each parent gets carried down to that child. And here is where the example comes in of earlier where I said the two columns can be the primary key, it's a compound key that are also foreign keys. Okay, so if I grab, oh, not that pocket. I brought my markers this week. All right, so we have table A, table B, table AB for now. Okay, and PKA, that's the worst K I've ever written, and PKB. All right, so these are our primary keys. In the child table, we'll have PKA, PKB, and it just so happens that this is a primary key. Okay. This is a primary key. These are, it's a compound primary key. that are also foreign keys. So when you talk about an intersection table, it's a primary key, that's a compound key. Why can I not write today? Made up of keys. Now, in theory, you're not limited to just two. You could actually have 3 or 4. You can have as many tables feeding into this intersection table as you want, and just the primary key, compound key will just keep growing and growing and growing with it. So, earlier when I was saying, a key can be any of these combined, well, in this case, it is. Now, the associative entity is the same thing, except it's the same idea as this. However, the foreign keys may not be participating in the primary key. It might have its own surrogate key of its own. It usually has multiple columns in it. So the perfect example for that is an invoice, okay? Or a receipt, Loblaws receipt. So you went to the grocery store, you bought yourself some bananas, and you bought yourself some bread, and you bought yourself some peanut butter, so you can have some peanut butter banana sandwiches. Okay? Now, when you go to check out, when you buy the peanut butter, you're not buying the store's peanut butter, you're buying one bottle of peanut butter. So what it's doing is it's associating the product peanut butter with your receipt. It's also going to count how much you paid at the time. So it's tracking how much you paid for it, how many of them you have. So for example, the example of bananas are sold by weight. They're not sold by the banana, right? So you buy bananas by the pound or by the kilo or whatever, method you want to use to weigh them. So you have a unit of measure, which in this case would be say kilograms. So you buy 1 kilo of bananas at 79 cents. So it'll be, 79 times 1. You buy 1.1 kilos, it'll be 79 times 1.1, and all that is tracked in the associative entity. Associative entity is the same thing as an intersection table, except it's got more. So it's got its own things that make it unique structurally to the rest. So if all you need to do is map out 2 items, and there's never anything extra, intersection table. If you're mapping the relationship between 2 tables and there's more information you need to track, it's an associative entity. Here's a spoiler. 95% of those tables are going to be associative entities. Rarely will you ever have just the 2. Not in modern systems, because in modern systems you need to know when was it added, who added it, when was it last modified, all that extra auditing stuff that needs to be on those records. The second you have that, it's an associative entity. So intersection tables were really common in the 80s, early 90s. And as people want more data because the hard drives got bigger, so we had more room for information, people started accumulating it that way. Yeah. Well, yeah, you can have half a dozen tables. As many tables as you want, as long as it makes sense. Obviously, you're not going to connect every table to every other table because that's stupid. But if you, for example, back to my order lines. So instead of being Loblaws, it's an Amazon order. And you put 4 things in your shopping cart and you check out. And I'm sure we've all had this experience where you buy 4 things from Amazon, they show up in 4 different boxes on 4 different days. So at that point, what happens is the tracking is per item. So in that case, you'll have the order ID to identify the order, how much it cost, the quantity that was bought, the shipping method is also tied onto there. There could be a few other things. Is this a gift, not a gift? Because you can choose that things are a gift, so there's no receipts or that kind of stuff on the order, or it comes anonymous kind of thing. Or there's a gift receipt put in whatever, so they can return it if needed. Yeah, so at that point you could have a bunch of things feeding into it. It's just whatever makes sense for the design. All right, so logical versus physical diagrams. I talked about that last week. Um, so logical and physical diagrams are very similar. Often database designers will skip the logical diagram. They'll go straight from conceptual to physical, skipping logical because of reasons. Um, Often the reason is you don't get to say what database engine you're working with. So for example, my division at Health Canada, if we need to create a new database, we don't get a vote on what database engine we're using. It's going to be Oracle. End of story. No questions asked. Like I once asked, can I use a MySQL database? They go, yeah, but they're going to charge us for it because that one has extra. Whereas Oracle, apparently the government buys this big, ginormous license and it doesn't actually cost us anything individually. But the MySQL, we pay per instance for it because there's so few at Health Canada for MySQL. Just saying, different groups will charge different things. So sometimes wherever you work, like at my old job before I joined the government, if somebody says we want to create a new database, the answer is going to be it's going to be on Postgres. Why? Because we were a Postgres shop. That was our default database. If we wanted to be MySQL, we'd go, okay, but justify it. So by default, we just designed a Postgres because they're both free. So what's the point of arguing of why would you argue for the worst product versus the better product, Um, so that's why often the database designers will skip the logical step because their situation is already enforced, right? You're going Health Canada, you're going to Oracle. My old job, you were going to Postgres. Other places, it's Microsoft SQL Server. No questions asked. That's what you're getting. So why take the time to do a logical diagram if you already know what where it's going? But there's also a lot of similarities, which is another reason why people tend to just skip the step. They both have tables. They both have relationships. They both have data types on their columns. However, one of the big differences, a logical diagram may allow the existence of many relationships. So if you create a logical diagram in some diagramming tools like Embarcado or ERWin or Power Designer, obviously you guys aren't using these tools here at the school because we can't get them for you for free. Power Designer is cheap. It's only $12,000 a seat. Just so you know, it's 12 grand just to get a basic license. It's a really good product. I've used it. It's really nice. I don't know if it's $12,000 nice, but it's really nice. It does a lot of really nice things for you. It's like Notepad versus an IDE, you know. So logical diagrams allow you to have many relationships. Physical diagrams don't. Logical diagrams will use generic data types. So for example, it'll do varchar. Whereas if you're doing varchar and you're working with Oracle, it's not varchar, it's varchar2. Because Oracle reserved varchar for some other purpose, so it's varchar2. Microsoft SQL Server, odds are you're going to use something called nvarchar instead of varchar. That is, nvarchar is for allowing other character sets other than Latinate. That means you can put Arabic in it, or you can put Cyrillic in it, or insert other alphabet. It won't cry if you try to feed it Chinese. Whereas if you take a database service designed with Latinate, it's not happy about receiving Chinese characters because it only uses 8 bits per character. And if I remember right, the simplified Chinese alphabet requires at least 2 bytes for every character. I think they're up to 3, depending which encoding system you're using. So yeah, that's the difference between logical and physical. They're basically the same thing, except one allows you to still keep your theoretical relationships, and one forces you to use specific engine-specific data types. All right. So The generic data types you will experience: car and varchar. So car and varchar are basically the same thing. Varchar stands for variable character. Back in the day, way back in the dark ages, before my time, car was the default data type for characters. Varchar didn't exist. Car, if you define something as a car 10, it means it will always occupy 10 bytes or 10 bits or whatever, 10 bytes. You put in the letter A, it still occupies 10 bytes. And this was important, going back to the dark ages, back in the computers when they used tape to tape instead of hard drives, when they were using magnetic media, because the system would know how far to move the tape for 10 bytes. So you'd read the field, then it goes, I don't need the next field. So you'd go 10 bytes, skip the field, and they'd know how many bytes, literally how many millimeters of tape per byte, how many bytes per millimeter, basically. It was actually a unit of measurement at one point, where different companies were showing off on how good their magnetic storage was by how many bytes can we store per millimeter of tape. That's really important because then the tape, the system could be fast in the sense that it knew exactly how much to move the tape every single time. Now, hard drives showed up to the party, and hard drives were big, 5 megabytes, 10 megabytes. Yeah, exactly, like the size of 2 pictures on your phone. And they were like the size of this desk. The problem was with those is that the number of bytes, the measurement stopped being how many bytes per millimeter of tape. It became how much data, how much did each megabyte cost you, right? So even nowadays, when you work in cloud solutions, you pay X amount of dollars per gigabyte of disk space you instantiate. So you open up you create a virtual drive, you create a database on on Amazon, AWS, and you say, I need a 100 gigabyte database. Well, I think if I remember, the first 20 gigabytes are basically free, but everything past that you pay extra for. So if they realized, hey, we're storing 10 bytes on this, and those 10 bytes are costing us 15 cents. We got to come up with a better way. So they invented variable character, where what it does, you define the maximum length it's allowed to be, but it only stores the data itself plus like a marker of some sort, like a couple of random garbage bytes that tells bits that say, oh, we stored the letter A, and then there's like a little marker that says, oh, this is the end of the data for this field. Now we can go to the next. Because hard drives don't need to move tape so many millimeters. They just seek. But now with SSDs, it doesn't even do that. It goes, just give me the data, and the drive goes, yeah, right? It's instant. So Varchar was a solution for the storage getting super expensive. Tape was a lot cheaper than hard drives, a lot slower, a lot less resilient. But so they created Varchar, so you can define something as Varchar 255. You put in the letter A, it holds 8 bytes plus a little bit, or 8 bits plus a little bit. We have text. Text is basically a big blob of text. Depending on the database server, it'll hold a lot of information. For example, in Postgres, the text field can hold up to the maximum size of a file on the operating system. So in theory, if I recall properly, a single text field in Postgres can be up to 4 gigabytes. Just one field. You'd never want to do that, but you could. Stupid if you do that, but you could. MySQL is special. It has 3 kinds of text fields. Short, tiny text, long text, I think it is off the top of my head, because they decided that people needed, better self-control. I don't know. Mind you, on other database servers, text is called other things. On Oracle, it's called CLOB, character large object. In Microsoft platforms, it's called Memo for whatever reason. But it's all the same thing. We have date, time. Those are the generic ones. Numeric and decimal, they're interchangeable. They do the same thing regardless of what platform you're on. In MySQL, you can use either, and they actually are the exact same thing. Floats and doubles, if you want lots of precision. Integers. All database servers give you multiple flavors of integers because integers can be big. So most of them will give you tiny int, and big int. I don't remember how big int is. It's something like 27 digits long. Like it's a big number. So those are the generic. You have platform specific ones like nvarchar. That's the one for Microsoft SQL Server. It lets you do nationalized character sets. Timestamp. MySQL Server has something called timestamp. It's a date time, but it sets it automatically every time the record is touched. On the other hand, Postgres also has something called timestamp. That's its version of date time. So you have to be careful. Text, I already explained the different flavors. Boolean. And MySQL is special. You'll notice I wrote special in a special way. MySQL doesn't support true Booleans. So Postgres, Microsoft SQL Server, Oracle, they support true Booleans. True, false, and null. Right? So realistically, Booleans in database servers are triphase Booleans, as in yes, no, I don't know. Okay, fairly straightforward. MySQL doesn't support true Booleans. MySQL has tiny int. You store your Booleans in a tiny int. And you used to be able to say tiny int 1, which meant it's a single digit tiny integer. Now it's 256. That's what tiny int cuts off, is a 256. It means that you have no, I don't know, and 256 versions of yes. So MySQL gives you a nuanced version of yes and no. But all you're ever going to store in it is 0, 1, or null. So, but you still have to use an integer. That means it takes up more room. There's tons of other platform-specific ones. Postgres has geometric data types where you can store circle in the database. And you actually feed it, X, Y, R. So you tell it, the circle starts here and the radius is this, and it knows it's a circle. And you can actually query against the radius, ask it which circles overlap to other circles. It's got data types for network stuff like IP addresses and MAC addresses built in. Oracle's got geometric ones also. It's also got, if you're willing to pay for it, it also has GIS data types, which it has to do with mapping. Different data platforms will give you different data types. I know Postgres has got something like 70 different data types, 60 different data types. You pick whatever works, or if you're really careful, you'd use as generic as possible so that it's easy to carry across. So use varchar instead of the fancy varchar. That way you know it's going to work everywhere. Okay, so physical diagram considerations. When you're creating physical diagrams, these are the things you should consider. Composite attributes should be broken down into their component pieces. Remember last week I talked about addresses and how that's a composite attribute where it's made up of multiple things. So an address should be broken down into its component pieces, which would be address 1, address 2, city, the region, whichever it's a province or state or whatever, postal code, country, and depending what part of the world you're in, you may actually have some extra pieces. I know in the UK for a while they had 2 city fields. I know he squinted at me when I said that because there's places in the UK that the address is some town near another town, and that's literally what you put in because the postal code covers like 3 towns. Because these tiny little hamlets out in the middle of nowhere, and they're all on top of each other, physically close to each other, but not right there. Postal codes might be different in different parts of the world. Try to make the data types and sizes reflect what's actually being stored. A lot of people are lazy and they'll just make everything a varchar 255 because why not? It only uses 255 characters. The thing is, you should make your your data as close to what it should be in the real world for a few reasons. If you're developing using a framework, often the framework will look at your database structure and use that as hints for its operating rules. So if you have a field called telephone number and it's set up to varchar 14, it won't let you type in a phone number more than 14 characters, so the framework knows it can't have more than that. Yes, you can make it big, but you should make it reflect what the data actually is. It's just, proper database etiquette, let's call it. Try to stick to generic data types whenever possible, so that if you need to, you've been working on MySQL and then your project blows up and it needs to go to an enterprise level database server, you don't need to take these weird data types that are MySQL specific and figure out how to make them work in another system. Or maybe your shop was Oracle this whole time and then, they can't afford Oracle anymore, so they're migrating you to Postgres. So if you're using all the generic data types, you have a lot less work for the migration. Avoid storing sensitive data whenever possible. If at all possible, don't store anything sensitive in the database. SIN numbers, credit card numbers, those are super sensitive pieces of information. Try to avoid storing that kind of thing. If you have to store it, encrypt it. Or maybe you don't need the whole thing. Like, sometimes you buy something online and then you look and it was bought on star, and then last 4 digits of the credit card number. All they're storing is the last 4 digits of the credit card number. That's not enough for someone to steal your credit card, but it's enough for you to know what card you bought it with, right? So you want to avoid storing sensitive data. If you have to store sensitive data, can you just store a part of it that makes it innocuous? And if you can't do that, find a way to encrypt it and limit access to it. Use reference tables as much as possible. Those are like, shipping methods, or use a reference table for countries. Don't let the person type in country. Whatever country, don't let them type it in. Make them pick it from a list. Why? Because humans are stupid. My third year system design prof had one big rule. Do not let your users type anything in unless you have to. And the job I had before I was at Health Canada, when I started there, I inherited a database. Let's call it a database, and I'm being really generous with this description. That was backed onto the internet. So this is back in the days of the internet, like, year 2000. So for some of you guys who weren't even around, just saying. And the forms where the people would sign up for stuff, let them type in their country. Now, most of our clientele was in North America, and most Canadian clients were pretty decent. They typed in Canada or they typed in CA. Stupid Americans, though. I saw America, United States of America, USA, US, U.S.A. US space of A. So I had to run reports, and I literally had to find every permutation of how an American would write United States. That's another one I didn't even mention, right? So that's an example of humans being stupid, because they're just going to type in whatever it was. Like in Canada, we had a bit of that problem at one point where we used to allow 3-character provinces instead of 2. Quebec was fine. Ontario was fine. Newfoundland. New Brunswick was pretty straightforward. They go NB. Newfoundland, we'd have NL, NFL, Newfoundland Labrador. And then we had the people that wanted to put in NFLD. Yeah, so we had a bit of that, but that got nipped pretty early in the mid '80s by Canada Post. Actually, Canada Post said no, and they fixed it for everybody. Um, so yeah, so for these kinds of instances, you want to use reference tables as much as humanly possible because that way you don't let the meat sacks type something in if they can pick it from a list. Yes, it adds a little bit of maintenance for someone that they have to make sure the lists are kept up to date. Cool. But how often do you have to add or take out a country? Well, depending what part of the world you're talking about, it's pretty regular. But most of the time, it doesn't change every single day. There's countries that keep changing names. Myanmar is a good example. They've changed names, what, 4 times in like, at one point, 4 times in 5 years or something. Or you have countries like Yugoslavia that no longer exist, which are now, what, 4 countries? 3 or 4 countries now? Right? You got Serbia, Croatia, Montenegro, and one other one. I can't remember what it's called. So Montenegro. Yeah. Bosnia. So yeah, that's the fourth. So they got four. Yugoslavia became 4 countries. So at one point, somebody would have to go in and update that list. Cool. Just keep it up to date, but it's not something you have to do every day. So use them as much as possible. It reduces the amount of data. It reduces the amount of typing. It makes the database design a little more complex, but overall, it's still better. Okay. When you're designing fields, there's a few common things you should do. For names, give at least 50 characters. Maybe you want to split first name and last names as applicable. Sometimes you don't want to because it's not important, but you probably want to split people's names into at least 2 pieces and allow at least 50 characters minimum combined, probably more than that. Because there's some parts of the world where people's names are freaking long. And then you got the Hispanic people, which insist on having like 14 first names. I laugh, but I had a student from Puerto Rico once, and he had 6 first names. And it became a game where I could call out any of his first six his names, and he would answer. And apparently, it was a thing in his family. Depending which name was said, he knew how much trouble he was in. But so you want to make sure you give lots of room for names. In general, 50 characters is enough for most names. If you're going to split it, give it 50 on each side. Use a varchar. It doesn't take up a lot of room, but don't. 255 is probably too much. Email. Always give it 100 characters. Consider making it a unique field while you're at it. And put the same email address in the database more than once. Did I tell you guys the story about the email address? One of my first job in Ottawa, when I inherited a database and they only had 75 characters for the email address. So I was working for Digital Equipment at the time. They got bought by Compaq and HP. So I was part of a division called User Application Support. I wrote their call tracking software. Well, I inherited the call tracking software, I should say. I didn't write it. I inherited it. And one day, one of the technicians came up to me and goes, I can't get this person's email address going to the database. It's giving me an error. Value too long. I'm like, I look at it, I go, okay, hang on. I go, it's 75 characters. I'm like, that's a lot. And I go, hang on, I'm on my way over. So I get up out of my cubicle and I walk down, at the other end of the building, go look at him. He goes, so here's the person's email address. So that email address convinced me to always use 100 characters. I usually do 150. So one of the clients for this particular group was the government of Ontario. So what happened is Digital Equipment would sell 1,000 computers to the organization or more, 10,000 computers. And based on the size of your order, you were given so many minutes a month of free tech support on your top 10 applications that your group uses. So instead of calling Microsoft if you're having a problem with Word, you'd call these people. And the thing, it was integrated into people's phone system. So Ottawa Hospital example is one of the clients. They could pick up the phone and they just type in an extension and it would ring the call center and bill its corners. And they'd answer going, Ottawa Hospital technical support. But no, they're actually working for digital. But that's how they'd answer. So Government of Ontario. So this email address was for a married woman from Quebec. Now, most people in this room don't know what that means. In Quebec, when people get married, the women get a hyphenated last name. They take their husband's last name, but they keep their own last name also. So they get their last name with a hyphen. She also had a hyphenated first name for whatever reason, a Bobby Ann kind of thing, but she had like a long ass first name. I don't remember what it was, but it was long. Like it was like imagine like Elizabeth Dash Dorothy. Something like that. No, it wasn't that, but it was long. Okay, but this gets worse. Yeah, like German words that are like that long because it's like 6 words glued together. So this person's first name, so the email address is a format of first name dot last name at, and I don't know why they thought this was a good idea. This is stupid Ontario government thing. They fixed this finally. It was the name of the department in English dash the name of the department in French dot on dot gov. So this person's hyphenated last name was 31 characters long. First name was something like 25 characters long, plus the period. Okay, 25 plus 35 plus 1. We're already at 61 characters of 75. At natural resources, das ressources naturelles, plus whatever the suffix was. It was done. Like the whole system just went, no. Emergency, Dan did an emergency patch that night. Had to fix the database, copy all the data to the new field, and update the applications to match. So, yeah, but that's just how it was, and you didn't have a choice. You sucked it up, and you dealt with it. But mind you, back then, a lot of people barely had email. So, money. Don't use money data types because they're not portable. Use numeric or decimal. The problem is that the money types are lossy. They lose precision because they always round to 2 decimal places. Most of you are thinking, well, look at Canadian money, dollars and .2 cents. How many of you have bought gas recently? How many digits of precision is the gas? 3 digits of precision. After the period, it goes 3. Before gas went to above $1, you'd often see 95.3 or 95.5. So it's 95.5 cents per liter. 3 units of precision. Most accounting systems do have 3 units of precision because of currency exchange. When you exchange $1 for the other dollar, often it's more than 2 decimal places of precision. And you want to, the more precise you have, the more accurate your foreign exchange gain and losses are going to be. So don't use money types, use a decimal instead. And that means it's also portable. Address columns can be challenging because depending on what part of the world you're in, things look different. Like Canadian and UK postal codes, they fit in the same spot. In Australia, they only have 5 characters in their postal code, not 6. You got Americans, again, stupid Americans. I don't know, some people make some really stupid decisions in their stuff in the States. So Americans at one point thought it was a good idea to have 5 digits for their postal codes. There's 90210, much like the TV series, right? 90210. It's the only American postal code I can ever remember. And I never watched it. I just the ads on TV all the time. So 90210. Now, that was great until you hit something like New York, where one postal code could be 5 million people. So then the postal carriers literally would get this stack of mail for 5 million people, and they'd have to manually sort them into the boroughs to deliver properly. So they said, oh, we'll be smart, we'll add substations. So now you'll have like 90210 dash up to 4 digits. They had to fix their postal codes because they were stupid. They could only have 99,999 postal codes. Sounds like a lot until you think about New York, LA, or San Francisco. I mean, even Toronto. Holy crap. Very dense. That means you need postal codes for smaller areas. So plan accordingly. If you're only ever going to be Canada, 6 characters is fine. If it's going to be international, you probably want to go to 10. That'll cover, even the Americans. And I know in some parts of the world, if I remember, like China, it's only numbers. Their postal codes are only numbers, if I remember correctly. There's no letters, just numbers. 6 digits. Because because you got Beijing. But that's not going to work. They're going to run out of numbers. Yeah, exactly. Beijing, Hong Kong, and Shenzhen, take your pick. It's like it doesn't work. So they've given, in some places, they've given up. So addresses can be challenging. So give yourself lots of room on the addresses, just to be on the safe side. Region, state, and province. Should you use the full name or just the ISO code? You should use reference tables whenever possible. Remember my little story about how stupid Americans were with filling out our forms. ISO codes are good because they're standardized. In case you're curious, ISO means Industry Standards Organization. They actually made a rule of what the letter codes are for every country and every region in every country. Normally, the region codes are 3 characters long. Country codes are 2 digits long. CA, US for the Americans, UK for the United Kingdom. Well, G, but there's actually a 2-digit code. There's a 2-letter code for it, which I think is just AG. I'm not 100% sure. There's, 239 of them. Okay, so I've just got just enough time to do last week's new physical next MySQL, and this is going to be lecture 4. Start modeling. Okay, now I also need ERD plus. And thankfully this one actually remembers me. Okay, so last week, right? Where we ended. Now I'm going to do this, but the physical version of it. So let's start out with our reference tables, because realistically, our reference tables are going to be our go-to anyways. So I'm going to drop a table. I'm going to call it genre. Now, people will argue about naming conventions. Some people say tables should be plural. Some people say it should be singular. I'm on the plural side of the argument because the genres table holds many instances of a single genre, so it holds many. Other people will say, well, no, it's a genre. Wherever you work, they'll tell you what the rule is. That's basically how it goes. Either it's singular or it's plural, but the thing is whatever you do, it has to be consistent for the entire database. If you decide to do one database as plural and one as singular, cool, don't mix match. So just stick to one. So I'm going to go genres. I'm going to add my ID, which is my primary key. And I'm going to add, gosh, let's call it genre name. Usually I don't do it quite like that, and this one's going to be a varchar. I don't know, what, 25 is enough? 30? Let's go with 30. Like this. And it's not allowed to be null. And I want to make this auto increment just so that it automatically counts. Okay, so here's my first one, happily created. I'll create my second one, which is the authors table. And I'm going to add columns. Again, that's going to be our ID. And it's a primary key. That's auto increment. We are going to go another one, which is the author name. Varchar 50, because I said at least 50 for a name. Realistically, you should break down first name, last name if you want, but it's fine. It's not null. Okay, and make it bigger. That I can. Uh, okay, I can kind of. Can I? Let's go like this and zoom in a little bit like that. Okay, so here's my two tables, genre and authors. I'll create my books table. Uh, Books, and I'm going to add a column again, ID, and it's a primary key, and I'm setting it to be auto increment. Okay, and I'm going to add the book name, uh, R100, because I've seen some books with some long names. All right, so far my data type selection is pretty straightforward, right? You know, genres can be pretty short. Want to make your names fairly long. I'm going to create my relationships, parent to child, parent to child, and now the tool is good. It created my foreign keys for me. So mind you, I'm going to go rename these so that they're not plural, which is, you know, just my preference. So if I go in here, oh, nope, that's not what I wanted. I'm going to click on this guy and go to these two columns and just rename them like this. So this is an associative entity. It associates two table. Well, at this point, it's an associative entity because it's actually associating two tables via the center. But it's not really because these are reference tables, but it looks like an associative entity. But there will be a true one in a minute. So we're gonna add another table called borrowers. Yep. Well, you'll see it in a second when I do the next batch. But it's this tool right here. Add new reference. Um, so I'm gonna add my ID for my borrower, and I go down to make it auto increment. And I'm gonna go the person's name, varchar 50, like such. Cool beans. All right. And I'm going to create two relationships for you in a second. So I'm going to go, next one is the lend table, right? Where the person borrowed the books. So I don't know, I'll call it lens for a lack of better word. Honestly, if depending on where you're working, they wouldn't actually let you call it something different. They make you call it like borrowers books or books borrowers so that the table, you know, makes sense to whatever it is. But in this case, the database design is simple enough that it'll still make sense. Usually when you use the name of the two parent tables in it, that really shows it as an associative or as an intersection table. So that's a lend. So I'm going to add an ID. Actually, you know what? I'm not going to add the ID. I'm going to make this one a true intersection table. I'm going to add the borrow date, which is date. And here's the thing. Whenever you track a date, you should usually just go date time. Because eventually somebody will want to know when during the day something was borrowed or bought. And if you just go pure date, you're only going to have the date. That means you can't make up data that hasn't been captured. So, and realistically, date time takes up almost no extra room. Return date, and that's going to be a date time. You'll notice that I didn't make the return time not null. Anybody want to take a guess why? So I didn't make the return date not null, as in return date is not required. They borrowed it, but they haven't returned it yet. You need to know when they borrowed it, but you don't know when it's been returned yet, so therefore it's allowed to be null. All right, now for the relationship. So right here, this tool here, add new reference, click on, take this, click and drag from one to the other, click and drag from the other, and it'll create the fields for you. And of course, I'm going to take the S's off because that's just me being me. Like the mandatory, not mandatory. So right now you can see these are all set as optional. Okay, these are not null, but now if I click on the relationship itself, that's just one of the issues. That's one of the issues with this particular software. It doesn't let you not make it optional because realistically in the database server, it's always optional. Conceptually, it's not optional, and I just got to remember, and I'll email Safraz to warn him that, because I don't think he's ever really used Vertibello. He's used something else. So it'll always show as optional. There's ways of making it mandatory in other design tools. But once you generate the database structure, it's still going to be optional anyways. Now, the fact that it's part of the primary key means it's not null. It's not null. That means it's going to be required anyways. But the relationship itself is optional. And that's literally, let's see if I can make this table a little bit bigger so you can see. There we go. And this is literally last week's done today. Um, the relationships are there. It's just I can't make it not. So if you come here, ID, see it's mandatory because it's mandatory because this shows. Why is it marking it as book ID? Which one am I looking at? Borrowers to lens, and now if I come here and I go optional, that means they're nullable. Interesting. But yeah, I mean here it shows that it's mandatory. Additional properties, no. Format, no. Yeah, there's not a spot for me to mark it as required, but that's just a limitation of the tool. If you use something like MySQL Workbench, you'd be able to do it in the tool. But it may not work on your Mac, so just saying. Okay, so I will export this as a PNG, generate, and download, and I'll post that as part of the example from tonight. What's cool also is you can generate this whole thing as SQL if you want to see what it's going to do. No errors. Type is not supported by the chosen database engine. Really? Oh, okay. There we go. Let's go do that again and generate and download. Come here and like this, and it generates the database structure for you. One of the advantages of using a tool. All right, folks. Hey, what the SQL was? Oh, nice. I guess I forgot to hit save or something. Good eye catching that, considering how fast I had that up on screen. But yeah, it should have fixed it. I don't know why. Usually does. So yeah. So next week, we're going to be talking about views and indexes. So a little more mechanical. Um, and yeah, that's it. We're done. Yay. Right on time. My parking expires in 3 minutes. I was gambling today. Okay.